And Dr. G, how do we submit our work?
So it has a little button inside the quiz that says submit work, but you should be able to do that after the quiz closes. So you could do it during the quiz, but you should use your time to work on the quiz and enter your answers. Go back afterwards and submit the work. And it's every question has a button to submit work, so only submit work on the ones that need work, obviously. So if there's one that's like other class, like I had one that was matching. And so there's really, I mean, with periodicity, is some, an alkali metal or a halogen. So there's work to submit, and I wonder if they're going to submit work for that. So either they all have a button to submit work or none of them do. Just make sure that you complete your answers and submit your answers in the timeline, and then do this. Then do the file upload of your images, the CAM scanner, for that work afterwards.
Could we upload just one file of work if all of the problems are clearly labeled?
Yeah, I think so.
There were a few of us that were still a little bit confused about what the different reaction orders represent in terms of the physical chemistry, not just the math. So perhaps we could discuss that in a little more detail.
Yeah, that's a great idea. But I think there were a couple phrases that showed where we could talk a little bit more. When determining the rate constant, the initial concentrations and their orders will affect the value of what? That'll affect the value of the rate, the overall rate. In fact, will the initial concentration affect the rate constant K?
This is where I was a little confused kind of about the wording of the question. So like in some cases we use the initial concentration to determine the K value, but within a given reaction, the concentration does not affect the K value.
So let me just write some notes in here, and this is just for what we have. A rate equals K times concentrations, for example, something like that. So this question's asking about the value of K. And so somebody mentioned we use the concentrations to find the K. We do, but that's from the data set. So we measure the rate, and we know the initial concentrations, and we use that information from that trial to calculate the K. But the K is really a portion of a proportionality constant. So we have a way to measure the rate, and we have developed the expression so that each reaction has one rate. That's how fast it goes. It's scaled to the stoichiometry. So it's a measurable rate. We can repeatedly measure that rate. We can look at the dependence on the initial concentrations, and then when we've nailed down that dependence, we can find K, the proportionality constant. So K tells us something about how fast the rate goes, right? If it's bigger, it goes faster. If it's smaller, it goes slower. So do the concentration of reactants affect the value of K? Do they determine the value of K? Mathematically, we use that information to solve for K, but that size of K, does that depend on those concentrations? It doesn't really. It does depend on temperature. Usually higher temperature is higher K, but that's not always that's not always the case. Usually it's the case, but not always. Endothermic or exothermic reaction, so heat might affect the rate differently, might affect that K value differently. But K depends on the temperature, clearly. Yeah, so the concentration and the order of the reactants help us solve for the value, but they don't actually determine the size of K. That's just a proportionality that's determined by the nature of that reaction, what those reactants are, how quickly they reach that activation barrier, how easy it is to get to that site where the reaction takes place. Yeah, so that was a good one I wanted to follow up on. And that was kind of related here. Explain. So K is the rate constant. Yeah, so that's more like I'm looking like we're looking for, this is empirical, right? It's experimentally determined value that tells us something about how fast the reaction goes. Someone was asking about first order and second order, like really the physical chemistry. What's a first order reaction? That depends just on one concentration. So what kind of a reaction typically would depend on just one thing?
Decomposition?
Yeah, decomposition is a really good example. That molecule falls apart under heat or under some other condition. Or, you know, maybe it's even interacting with another substance, but it doesn't depend on how much substance of that is there. Second order reaction, how does that represent a reaction physically? Yeah, and so in terms of collision theory, what would it mean to be second order? I mean, just physically, what's one way we would get something to be second order? Like if those two things have to come together. So you have a concentration of one thing and the concentration of something else, and they have to collide, then that might be a physical explanation for why the rate would be second order.
Maybe a more complex structure?
Yeah, like maybe if it was A times B squared, maybe B has to form a dimer before it's ready to react with A. So just thinking, these questions are sort of just to get discussion going and be thinking physically. It's great when you can just solve the math, and that'll get you really far. But also being able to interpret it on a particle level is really one of the deeper ways to answer these questions. Okay, so I'm going to go forward from page 31, thinking about mechanisms. All right, here we are, reaction mechanisms. So a mechanism is a series of steps. What we're trying to find out is exactly what particles come together when the reaction happens. And we get at that information by measuring the rate and playing with the concentrations. So here's an example reaction, an overall reaction, the NO2 plus CO goes to NO and CO2. But we don't know exactly how that happens. So we're going to propose a series of steps, which is just a guess. And then, like everything in science, we're going to test it and find out if it is consistent with the rate law. If it is not consistent with the rate law, then we throw it out. If it is consistent with the rate law, then maybe it describes what happens. But we, of course, can't ever prove for sure that it's true. We just collect different information that indicates that it might be true. Okay, so if the reaction shown is the actual collisions, these things come together and turn into that, then it is an elementary step. So an elementary step in the mechanism is what we are proposing is literally the way the molecules come together to form the products. So in this case, we're going to look at this in detail. In the first case, we're looking at the idea that the two NO2 molecules come together and transfer an oxygen. And then that NO3 goes on to connect with the CO2. The CO has a collision with the CO and transfers one of its oxygens to form CO2. So that would be a mechanism that could work because it adds up to the overall reaction. So that's a precondition. We always need our steps to add up to the overall reaction. All right, so these are the two steps. They're all whizzing around in the gas phase, which is why they're blurry like that. So intermediate is something that is formed and then consumed. So the NO3, it gets formed in the first step and used up in the second step, and it does not appear in the overall reaction. So that would be the intermediate. That was NO3, formed step. All right, as we look at the elementary steps, we're going to talk about the molecularity. So that's the number of things that come together to make that happen. So in the case of this ozone just decomposing, and then the asterisks, of course, this is showing us that it's an excited state. So it doesn't normally just decompose, but maybe in this case it had just absorbed some light and it's about to decompose. But that's just the ozone breaking down on its own at that point. So that's unimolecular, just one thing. So that would be like a first order in ozone. It would be unimolecular. If it's bimolecular, then there's a collision between two molecules. So that would be two reactants colliding, bimolecular. Termolecular would be a three-body problem. There aren't that many reactions that happen in a reasonable time scale that are termolecular. It does happen some, but usually two come together and then the third one joins. They're usually at least a little bit separated in space. So this is highly improbable, but it does sometimes happen. But usually we'll be looking at unimolecular and bimolecular mechanisms. So if we have an elementary step, then the rate law follows the stoichiometry. So if the reaction is an elementary step, then we can just use the stoichiometry to write the rate law. Now, of course, we might guess that at some point, but we would use experimental evidence to confirm it. The thing is, with an elementary step, we may not have access. If it has an intermediate in it, we may not have access to that initial concentration because there's no way you can put in an initial concentration of that intermediate, like the NO3. So there are a couple things that have to happen for something to be a valid mechanism. It has to sum to the overall balanced equation, and it has to agree with the experimentally determined rate law. And that is all we have to really determine what our mechanisms are. Now, reactions, have you worked with reactions like equations where you can just add them up?
Yes.
Cancel everything out, line up your arrows, cancel everything out. That cancels. Consider some experimental results that say this is our rate law, right? So we've measured that. And step one shows those two NO2s. Then that could be a valid mechanism, right? Because it agrees with the experimentally determined rate law. But if you have more than one step, then you have to look at the rate determining step. That's where we're going to be able to measure, right? So there's going to be a slow step that determines the rate. So we don't necessarily know. Now, if step one is as written and that agrees with our rate law, then this could be the mechanism. And step two could be a fast step. So we haven't really verified step two, but it seems likely that it could work. So let's go through a couple examples where we try this. Now we have K1 and K2. And when we start looking at reactions where we have two-way reactions, which we're going to do a lot of in the next chapter, we'll have like K in the forward direction and then K in the reverse direction. Or a lot of times we'll say K1 and K minus 1.
Professor, quick question. When we're talking about slow and fast, what exactly are we talking about there?
Just relative to each other. So the overall reaction, the rate will be determined by whatever is the slow step, and it depends on the reaction. So it's just like pouring something out of a bottle. The bottleneck is the slow part. If you were to just like take a 2 liter and cut off the little neck, you can pour stuff out much faster. So the slow step is just the slowest one that determines the rate.
And how are we determining which one is the slow one?
We're gonna
Is it
find.
always step one? Oh, okay.
It's not always step one,
Okay.
but it might be hard to measure step one if one is fast and two is slow, because we'll be able to measure step two because it's a slow one.
Will you usually just give us which one's slow and which one's fast?
Yes.
Okay.
Or you might have a rate law and be able to figure it out from that rate law.
Mm.
But usually we'll just give it and work with what we have there. So here, determine the rate law for the reaction. So if we're saying this has the following mechanisms, then these must be what? They must be elementary step. So that's what we're proposing. Let's say that these are the elementary steps. Then the rate law is going to be determined by this one. So go ahead and write that rate law. So if it's an elementary step, then we can just write the rate law from the stoichiometry for the slow step. Then once you have that NOCl2, it's going to react quickly in the second step with NO to form products. So what is NOCl2?
An intermediate.
The intermediate.
Okay, so let's sketch an energy diagram for this reaction. So remember, if this is a slow step, what do we know about the activation energy?
Is it going to be higher?
Yeah, higher than what?
Pretty high.
The fast step.
Yeah, it's going to be greater than EA2. And so what does that mean about how many lumps there are in your diagram? No, there's going to be 2. So you're going to have 2 barriers for a 2-step reaction. All right, are reactants higher or lower than products?
It depends on if it's exo or endothermic, right?
We have a delta H is minus 77.2 kilograms.
Ah, yeah. So it'd be exothermic. So I think reactants would be higher.
Wait, Dr. Gibbons, for the rate law, wouldn't the NO be squared?
If it only depends on step one, then we only have 1 mole, I guess, of NO in that case.
That's right. So the one that was squared was this reaction where we had these 2. And we've got the squared there, but we're looking at a different reaction. Now we're looking at the NO plus Cl2. And so it's not squared in that case because our rate law is going to be determined by only the slow step. So we do have this other NO, but we can't measure that because it's in a fast step after the slow step. Okay, so we have an exothermic reaction. So I'm going to put my reactants here. And then I'm going to put my products here. My first activation barrier has to be pretty high. So I'm going to just draw this way up here. And then there's some second one. For example, this right here will be EA1. And where's EA2? And where's the bottom line on that one? Yeah, so there's a little valley in there. That would be the intermediate. NOCl2 there. Right, that's our intermediate. And then let's go ahead and put our heat in there as well. All right, do we cover everything? Sketch the diagram, account for the number of steps so you can see that there's 2 steps and the first one's the slow step. Okay, so let's take a look at this one. here's our rate law. What is the rate determining step? You know, I usually write the rate law for each elementary step just to have it visible. So I'll label it step 1, rate 2. So that clearly matches the first one. All right, so similar to the previous equation. And that's pretty low. All right, does that make sense? Look at my old notes, show I've got a typo on here. This 2 shouldn't be there. It's just not balanced. It's just a typo in the balancing. There is a 2 right here.
What would be the difference then?
It was just that, like if we add these together, then we would have 2 N2O plus O. Oh, but these are going to cancel. Goes to N2 plus N2 plus O2. So that matches our original equation. It's just that it's just a typo that there was a 2 there. So there is a 2 in the original equation, but there's not a 2 in the step 2. All right, let's look at the next one. I think we're just about getting to the part that is not explained in the textbook. Number 3 still is. Number 3 is pretty much the same, just what we've been doing. So we have a fast step and a slow step. So what should be our rate? I'll just go ahead and write both steps.
That should be...
Yeah, this one's a little more complicated, isn't it? So just using the slow step as our rate determining step, we think that the rate overall is the second one. But there's N2O2 in there. Can we do method of initial rates with that? We can't. Right, that's an intermediate. That means we can't just initially control the amount of N2O2 we put in there. So we won't ever have an intermediate showing up in the overall rate law. So down below here we give the experimentally determined rate law has NO squared and O2. So does that match? Well, one has N2O2 and one has NO2. So what we're going to do is make these match. We're going to make these the same. Because we have that intermediate showing up, we have to rearrange our rate laws to get rid of it. So you can only include concentrations of reactants. You can't have a rate that depends on something that doesn't even show up as a reactant, but it has to have the reactants in it. Here we're going to introduce a reversible fast step. And then I can write the reaction for that fast step. So what that's saying is that that step 1 comes to equilibrium before step 2 even gets going. And that's what it means to be fast. So I'll write that rate. So now I'm going to write rate 1 equals K1NO squared, right? That's the same as what I had. But now I'm going to write the rate in the other direction. I guess we haven't done equilibrium yet, but at equilibrium, which I like to give a little symbol like that. It's like a Mobius that's not closed. At equilibrium, the rate in the forward direction equals the rate in the reverse direction, right? Because they come to equilibrium, then they're matched. Right? As soon as the products form, they start to react back to reactants. And that establishes an equal forward-backward rate before step 2 even gets going. So the rate in the reverse direction is K, oh, this is a K1, this is a K minus 1. And now in the back direction, now N2, O2 would be the reactant in the reverse reaction. So what I want to do is find a way to get rid of the intermediate in here. So I'm going to solve this for that concentration and plug it in. So I have K1 times NO squared over K minus 1. Now I'm going to plug that in there. Okay, do you see how that worked? Now, of course, those rate constants, all those Ks, we have them designated for which process they refer to. But ultimately, when we measure them, it's just a proportionality constant. So we're going to roll them all into one value. We make the assumption that the fast equilibrium reaches equilibrium before the slow step. So we'll talk a lot more about that in the next chapter. We might also write this again, that the rate is some new K, K prime, NO squared O2. So that matches our experimentally determined rate law, and we can derive it from these two steps. I think I just did all the work that was supposed to be below. Okay, so writing the rate law for the forward reaction in the elementary step, we had that. And write the rate law for the reverse rate. So that's this one. Yeah, I just wrote it up on that by the equation. All right, so now let's see, I'm going to plug that in to, this was the reaction for the slow step right here. So just looking at the slow step, I'm going to rewrite that one. And then I'll plug that in here. We'll give that a new value, K prime. And then does that match our experimentally determined one? Does. That was given right up here at the top. NO squared O2. Okay. Have a good weekend, everyone.